To those of you who weren't here before, I'm Simon Kemmerling. I'm from Fraunhofer ICT in Germany, and we were in charge of producing the polyglycolic acid based on the glycolic acid of what we heard just about before, which was produced at Kemmerling Institute from starting from the ethylene glycol. So next slide, please. Okay, so just a little bit of background to the chemistry behind our PGA and what we are targeting in the REFUCOAT project. On the top, you can see both ways to produce a PGA. So the first one is the ring opening polymerization. So first, the formation of an oligomer. So oligomeric polyglycolic acid, depolymerization, cycling depolymerization to a glycolide, and then going on to a PGA from there on. And the second alternative would be a direct polycondensation just based on glycolic acid, or even an oligomer, in this case, an oligomer of polyglycolic acid already. So the idea of what we had during a REFUCOAT project was to go the direct way through a polycondensation instead of the ring opening polymerization, based on literature reported trials which were leading to high molecular weight, highly viscous or solid polyglycolic acid. Next slide, please. Okay, so to start the process, we were starting in batch scale and laboratory scale first to ensure we have good processing conditions, be it temperature, pressure, so the vacuum we are drawing, the reaction time, to start with very small amounts of material for not wasting any and keeping the amount of material necessary basically to a minimum, and have the possibility to do a lot of experiments with different catalysts, also with different catalyst system, to ensure, okay, if we want to grow this process from really small scale to a little bit bigger, to pilot scale, and maybe even later on to industrial scale, that we would have fitting conditions for this one. So on the right side, you can see a very small lab setup for these batch experiments to first get the process started, to start from technical grade glycolic acid, just as the one that Kemmerling Institute was producing, like a 70% concentrated solution, which is available, and then going from there on, testing out if the removal of the water, first from the 70% solution, is able to be removed, as well as, of course, the resulting water from the condensation reaction, which, of course, has to be removed in order to shift the equilibrium of the reaction from the monomers or oligomers to the finalized polymer in the end. And on the next slide, then you can see the next step basically. So we were transferring or trying to transfer our process, which we obtained in the batch lab scale, to a little bit bigger scale and to a continuous plant, because if you want to scale up a process to several kg or even in the future hundreds of kg per hour, you have to have a continuous process to have it economically friendly, energy efficient, and of course a controllable process. So even here, the same issues and the same requirements to the process were applied. So it has had to be make sure the water is removed. A long residence time, even for a continuous process, has to be ensured, because polycondensation reaction is rather slow. The process has to be able to handle the catalyst content, so the solid catalyst, in a in a low viscosity liquid, which is the monomers or oligomers, pull vacuum, and even have the throughputs in the meantime. So we were settling here for a short path evaporator to first remove the water from the 70% solution, and then attached to this one, which you can see on the bottom side of the picture, plug flow reactor, so a heated pipe basically, to have a lot of residence time and let the reaction continue through this equipment. And with this equipment, we were able to produce oligomers of around 5 to 10 units of glycolic acid. And then on the next slide, you can see the next step to go further, to increase the molecular weight further in order to produce a material which then in the end has the properties to be processable in the printing or in the printing equipment to produce a barrier property having structure, a foil in the end, a packaging foil. So this equipment we chose for an extruder to be able to handle the rise in viscosity, first starting from the low viscosity liquid and then having it growing over the course of the reaction itself to in the end have a polymer. And of course, in addition comes again the removal of water, now just from the condensation reaction, as well as being able to, for example, add additives which give for thermal stabilizing, or even some processing additives for the later on continuing processing to produce the foil which we in the end want to have for the product, for the final packaging. And then on the last slide, you can see a comparison of all these different processes. So we elaborated a bit on the lab polycondensation, the short path evaporator, and the post-heating. Post-heating means that tube that you have seen to extend the residence time in the reactor, and the reactive extrusion, and also compared this to the literature of laboratory ring opening polymerization. So starting from a glycolide, the cyclic dimer of the glycolic acid. In terms of throughput, so how high can you go in throughput? Scalability, if you want to scale up from lab to pilot or even industrial scale, which molecular weights of the product can be used, and the catalyst. So a short explanation about the catalyst. This means how available is the catalyst? Is it biodegradable, which would be, of course, a plus in this case, or even toxic, and can it be removed? And for this, for us, the basic outcome of this slide is that the combination of the short path evaporator and post-heating to start the reaction to get oligomers, and then the extrusion process to finish basically the final polymer afterwards, was the go-to solution that we went for within REFUCOAT project to get a polyglycolic acid, which then can be used for a packaging application.